Hello, today's video lesson is on titrations. We're going to look at what titrations are. I'm going to talk about how we use titrations, and I'm also going to talk about the three general types of titrations that you're going to see. At minimum, what a titration is a controlled buffer system, is really what we're dealing with here. We're going to use this thing called a burette to analyze a substance. Okay, so our tool here that we use is the burette. Down here in this flask, what we're going to do is we're going to put down our substance that we're going to be measuring or analyzing. Okay, so this down here is what we would call our analyte because it's what's being analyzed, and up here would be called our titrant because it's the substance that we're using for the titration. Okay, so that would be our titrant. Alright, so what do we do with these? One, we can find the concentrations of acids or bases in solution. So if I don't know what the concentration is of an unknown solution, which you're going to do, you'll do that in a lab, you'll figure out what the concentration is. You did that in honors chemistry as well. The next lab we're going to do is actually to find the Ka of an unknown acid, and that would be another way we would use a titration. Find the molar mass of an unknown compound, oxidation state of metal ions. I mean, there's a lot of uses for these titrations. So we will actually do if not all of these, definitely the first two, and most likely the other two, depending on how much time we have second semester. Alright, so what happens during a titration is as we add, first of all, most of the time what we put in here would be something like sodium hydroxide. Okay, we would put sodium hydroxide would be our titrant. What we do is we add the titrant to our analyte, and our analyte tends to be some kind of acid compound. Okay, so what happens is as I add the base, the reaction happens and my pH changes. So if I have a base up here and an acid down here, my pH starts out pretty low, and as I add the base, my pH starts to go up and up and up. So what I'm going to do is I'm going to analyze my pH as I add more and more of the titrant to my solution. What I'm going to do is I'm going to talk about the three types of titrations: the strong acid, strong base. So that means that I would have strong acid here, strong base up here, strong acid down here, and see how they react and look at what happens as I add the substances. Then we'll do is we'll look at a weak acid. So I'll substitute a weak acid in here and then do the titration, and then the last one is I substitute this with a strong acid and put a base down here, in this case a weak base, and do the titration as well. Okay, the two that are the hardest are these two here. This is the one we did in honors chemistry, so we dealt with this in honors chemistry. This is pretty much very general stuff. Okay, so let's take a look at all three types one at a time. The one we're going to look at is a strong acid being titrated with a strong base. So again, as I said here, we're going to have sodium hydroxide. It's going to be my strong base, and in here inside the analyte, what I'll have is HCl. Now I'm going to stay away from doing calculations here. What I'm going to be doing is really talking more about the reactions that are going to go on inside of the container, and talk about the background and look at what's called a pH graph, okay, or a pH curve. Alright, so what I'm going to do here is I'm going to plot the milliliters of sodium hydroxide, and what I'm going to plot up here is my pH. Okay, so before I do anything, I'm going to measure the pH. My pH, because I have a strong acid, is going to be really low. So it's going to be really low down here at the beginning. Now as I add the base to this, what's going to happen is I'm going to get a chemical reaction, and the reaction I'll have is based on the fact that I have, actually what I should do is list the species present, right? So let's see what species I would have here. In the beginning, I just have H+, Cl-, and water. So this is nothing more than a strong acid problem. So all I would do is take the concentration of the hydrogen ion, take the negative log of that, and I would get my pH. The nice thing about these types of titrations is that there is no equilibrium, because what we're going to have is all strong acid, strong base stuff, so therefore no equilibrium is going to be found. Okay, so we do no ice table. Okay, no ice table. Everything we do here will be a BCA table because we're going to be dealing with stoichiometry. Okay, so everything's going to be stoichiometry. Alright, so the first thing I do is I calculate the pH of the solution with just nothing added. No sodium hydroxide added. pH is down here really low. Let's say like 1.2 or something. Okay, now then I add the sodium hydroxide. Well, what I have is Na plus and OH minus. Alright, well, if I analyze what I have here, I have an acid, I don't care about the chloride. Water, yeah, it could do something, but in this case, again, it's not. Sodium ions don't do anything, and I have a base. So what's going to happen is these two are going to react together. So what I have is hydrogen ions plus hydroxide ions gives me water. So all I do here is a BCA table, and I figure out which one I have and which one I have at the end. So it's see how much of the hydrogen and how much of the hydroxide. Well, depending on which one runs out, let's say the hydroxide runs out, I have excess acid here, right? This is the excess reactant, and this is my limiting reactant. The solution is still going to be acidic, so therefore it's going to go up, but it's not going to go up drastically. So I'm going to get as a point here. All right, I'm going to keep doing this and keep doing this and keep doing this, and eventually what happens is the system is going to eventually, more and more of the hydroxide is going to get added to this. I'm going to have less and less acid. So eventually I'm going to get to a point where this no longer is my excess reactant, but they'll both be the limiting reactant. That's a special point. Okay, so if I keep doing this, this curve is going to look like this, and then all of a sudden it's going to go up. Whoops. Curve's going to go like this, and then all of a sudden it's going to go up, and boom. And this is typically what our curve looks like. Probably a little bit more of a curve right in here, but you get the idea. Okay? So what we have down here is our acid, is what we have down here at this portion. Up here we have our strong base dominating, and in the middle here, right here is what we call the equivalence point. I don't like to call this the neutralization point. I prefer to call it the equivalence point because this isn't always going to have a pH of 7. But for these particular problems, the pH will be 7 for these. So when we get to the equivalence point of a strong acid, strong base titration, the equivalence point is going to be equal to 7. Why? Because when we get to the equivalence point, what are we going to have left? Well, if we list the species present, these are gone. What we're going to have left is chloride ions, water, and sodium ions. Well, we know that the chloride ions don't do anything to water, and we know that the sodium ions don't do anything to water. The only thing that's there is just the water and two ions, a cation and an anion, that have no effect on the pH. If you remember, we talked about hydrolysis of salts, so therefore we have a neutral solution. Okay, and then if I continue on beyond that, then this becomes my excess reactant, and this becomes my limiting reactant, and therefore I have a base left over, and my pH goes over 7. So very general, type of titration: strong acid, strong base titration. So let's take a look at what happens if I switch this strong acid out and put in a weak acid. Okay, actually before I move on to the next type, I wanted to mention one other thing. What if I flip-flop these? What if I put my sodium hydroxide down here and I put a strong acid here? How would that play out? Well, it's going to be the same thing, just the opposite direction. So what I would have here is milliliters of HCl that I would add at the bottom, and on the top I would still be looking at pH. I'm always going to be looking at pH. And what I would have is it would look the opposite. I would have it start out with a base, and then all of a sudden it would drastically drop, and then I would get my acid. So it would be the inverse of the other reaction that I saw. So I'm not going to keep doing this and showing you the opposite. You can probably figure out what happens once I figure out, one way. You can flip it over and see what happens with the second one. Okay, so now let's go ahead and take a look at the weak acid, strong base titration. Okay, since I have a weak acid that's being added to this, it's going to change things up quite a bit. So let's say that I have hydrofluoric, just because it's the easiest weak acid to write, and I'm going to titrate that. My titrant that I will use will be sodium hydroxide. Okay, and as I said, in a later video I'll do the actual numerical calculations. Right now we're just looking at the logic of what's going on. Alright, so right now in the beginning, my species that I have present, before I add any of the sodium hydroxide, what I have in that solution is HF and water. Right? I just have the hydrofluoric. It's a weak acid, so it doesn't dissociate to any great degree, so I keep it like this. This is with no sodium hydroxide added. Okay? So the milliliters equal 0. Okay? Well, since I have hydrofluoric acid, this is a weak acid, this is going to be just your traditional weak acid problem. You're just going to take your concentration of whatever the weak acid is in the container, plug this in, solve this here, and you end up with just doing a simple ice table, okay, and then a Ka. I'm not going to do this, of course, and you would solve for X, which is equal to hydrogen concentration, and find your pH. Typical problem that we've been doing so far. Nothing different here. Nothing different here. So that's what you do in the beginning. Now, after you add the first drop, okay, so when the volume here, when the milliliters is now greater than 0, what we create is a buffer. We're going to create a buffer. Okay, why is that? Well, let's take a look at what happens to see why a buffer forms. Let me erase this. Okay, so after adding the sodium hydroxide to the hydrofluoric acid, let's take a look at the species that we have present. Well, we have hydrofluoric acid, we have water, and what we're going to do is we're going to add sodium ions and hydroxide ions. Okay, so what's going on here is I'm going to have an acid. Again, how do I know? I'm just identifying what I have. I have an acid here. Water's neutral. It's going to it will do something, so please be patient. It will do something. The sodium ion, and then the base. Okay, so I've got a weak acid and I have a strong base being added, so of course these two are going to react together. Acids react with the bases. So hydrofluoric acid is going to react with OH minus. Now as soon as I introduce OH minus, as soon as I add hydrogen ions, that means that there is no equilibrium. So whenever you see these strong acids, strong bases added to the solution, no equilibrium, we're going to use a BCA table. This should be very familiar to you from the stuff that we did with buffers. So this makes water, and look at this, it leaves behind the fluoride ion. Originally all I had in here was hydrofluoric acid. When I finish this, okay, I'm going to have some of the acid here, I'm going to have some base here. These are going to change by X and change by X and go up by X and go up by X. Well, initially this is going to run out. This will be our limiting reactant. So here we're going to have some of the acid left over, and we're going to start to create the base. Right? So our base is going to go up. So what happens is our concentration of the acid goes down, and the concentration of our anion goes up in these reactions. So we start to see that after we've added the first drop of base, what we're left with afterwards. Now if we think about listing the species that are left over, what we have left over is HF, hydrofluoric acid, still have that water there, and we still have sodium ions. Now what we've introduced are fluoride ions. And that should ring a bell for you. That should hopefully indicate, here I have an acid and I have a base. And you could say, well, wait a minute, won't they react together? Well, I guess you could say that, but they're conjugates of each other, right? If I have a weak acid and a conjugate base of the weak acid, this is your buffer. So what I have done is I've buffered my own solution by doing this. And this is going to have a big impact here. Okay, so now to find my pH, what I do is I take the results of this, what I have is an after, and as an after, and I plug that into the ice table. Now you guys know better than that at this point. What you can then do is use, instead of the ice table, you can use the Henderson-Hasselbalch equation. Right, so if you have a buffer system, you can start using the Henderson-Hasselbalch equation. This cannot be used at the first drop. Okay, it can only be used once the buffer is established. Okay, all right. So we've got the basic idea. Now, what's going to happen is this is going to keep going on. I'm going to keep adding more base. I'm going to add some more base to this, drop by drop by drop, and every drop that I add is going to add more and more and more, and eventually this is going to run out and this is going to run out. You're going to get to the point where they both get to what's called the equivalence point, and as that happens, this gets lower and lower and lower, while this gets bigger and bigger and bigger. Okay, so let's take a look at what the titration curve would look like. Okay, so if we have the volume of the sodium hydroxide being added here, and my pH here, okay, it's going to look kind of like the same curve that I had. It's going to have this distinct curve here, and this going up, and then going like this. Okay, now when we look at this curve, a number of things are going to happen along this titration curve. A couple key points. First of all, in the beginning, at volume equals 0, no buffer, and you cannot use Henderson-Hasselbalch. So no Henderson-Hasselbalch at that equation. Only thing you can use there is the ice table. So it's just a weak acid, just a simple weak acid problem. That's it, weak acid calculation. Okay. Now as you go along here, think about what's happening in this reaction. Let's write the reaction down here again. H fluoride, right, reacting with the OH minus. Okay. What it's going to do is it's going to keep creating water and HF minus. Now this starts off as 0. If I use the BCA table here. Okay, so let's say that this was, let's just say for make it easy, let's just say it's 10 molar, 10 moles here. All right, if I originally add 5 moles here, this is going to go down by X, this is going to go down by X, this is going to go up by X, and up by X. Well, this is going to run out and go to 0. Isn't this going to go to 5 moles here? And this is going to go to 5 moles. Right, as this number gets bigger and bigger and bigger, my amount of acid is going to keep getting smaller and smaller and smaller, and therefore my pH is going to keep going up because I keep getting more of the acid, or I'm sorry, more of the base. You can also see this in the Henderson-Hasselbalch equation, right? pKa plus the log of the base over the acid. As the base gets greater, your pH starts to get greater. Okay. Well, at this point here, if these two are the same, hopefully remember that that's called an optimal buffer. It's an optimal buffer. And that point is going to be what's called the halfway point of our titration. I'm going to say that goes right here. That's what's called the halfway point. Halfway point. And this is where you have an optimal buffer. And at this point here, you have the pH is equal to pKa. Remember we talked about that before. pH is equal to pKa. That happens right here at this point, at that halfway point. Now again, you're going to have an equivalence point, and that equivalence point is going to be, you know, another half of that way from there. So that's why this is the halfway point, because you're halfway finished. Why? Because you're going to take out the other half of this and make this go to 0. So let me show you that part. So if I continue to add the hydroxide, I'm going to get to a point where these are both going to be equal to each other. This will drop out, and this is going to go to 10 moles. Okay? That is called the equivalence point. That's your equivalence point. We call it the equivalence point because our acid and our base are at equivalence to each other. The strong acid, the strong base that's added is equivalent to the amount of moles of the hydrofluoric acid. We don't want to call this a neutralization point. Absolutely don't want to call it neutralization. So let me explain why. Let's think about the species at this point when we get to the equivalence point. So we get to the equivalence point. What are the species that we would have present at that point? Okay, hydrofluoric is gone. OH is gone. Well, we have water. That's definitely there. And we know that we have that sodium ion from the hydroxide, and what's left behind is that fluoride. So what's going to happen here is that fluoride ion is now going to react with the water. So at the equivalence point, you have hydrolysis of a salt. You're going to have that hydrolysis of a salt occur. So what that means is that that fluoride ion is going to react with the water, and you're going to end up having a reaction equilibrium where this forms HF and it forms your OH minus. So it's going to make it basic. Did everybody see that? Hopefully you can kind of see what I'm talking about here. At the equivalence point, because I have that fluoride ion left over and it's a conjugate base and it's effective and it's going to take that hydrogen ion, it's going to create a base. So when we get to the equivalence point here for this, our equivalence point is basic. So this is going to be greater than 7. So our pH of 7 is here. This actually crosses over above 7. Hence why I hate calling this a neutralization point or a neutralization reaction, because actually at equivalence we have a basic solution. And again, you can do the ice table here, right, to figure this out. You can no longer use the Henderson-Hasselbalch equation, because in this region here, from right here all the way through here, right before that point is where you have the buffer. So here's where you have your buffer. And what you can do there is you can use the Henderson-Hasselbalch equation for this whole section. Okay. At this point here, at this red point, you have to do hydrolysis of salts. Okay, it's hydrolysis of salts. Now if I continue on and I make this 11 moles, by adding a little bit more, this now becomes excess. And now, if this is my excess reactant, what that means is I have a strong base dominating the rest of this problem. And the rest of this here becomes strong base. Okay, so that's kind of a breakdown of a weak acid strong base titration. Now, wanted to go into the third type, but I think I'm going to have to hold off just because I know you're going to get upset with me because this video is already way too long. So I'm going to stop here and I'll do the weak base strong acid titration in a second video. Alright, thanks a lot guys. I'll see you later.